Hi. We're at the point of the year where we've done some things with force, obviously, and whether you teach forces before motion or motion before forces, in terms of the study of motion is called kinematics, is really a personal choice among physics teachers, and there's merits to both ways. So we've studied forces before motion, but with the online labs that are available, we have to have a little bit of understanding about some of the mathematical applications of motion in order for you to understand them pretty well. So I want to just put a couple things up here. It's going to be important for you to understand these as we go through some of the online simulations with Pivot Interactives. So hopefully you recognize this as Newton's second law. Acceleration of an object depends on the net force on that object and the total mass of whatever is accelerating. So if you have one object, that mass is easy to understand. If you have multiple objects connected to each other that are accelerating, you've got to take the mass of the entire system. If you remember, another version of Newton's law, second law, is F net equals m total times a. So this is just an algebraic rearrangement, and this should already be on your formula sheet. So that's nothing that's new. What is new, though, is that we can use our study of motion to figure out acceleration if we don't know the mass and the total force. Sometimes we can use that acceleration then to tell us things about the mass or the net force on an accelerating object. So it probably makes sense if you understand that acceleration is the rate at which velocity changes, that one way we could figure out acceleration is change in velocity, and remember the Greek triangle symbol as delta, and that means change in so change in velocity over change in time. A lot of times you'll see that as Vf minus Vi over t. So I'm not sure if I like this notation as much, but it's quite common. Vf is final velocity, Vi is initial velocity, t really means delta t, or time interval. So if we look at acceleration as delta v over delta t, hopefully that's something that kind of makes sense. We could rearrange that if we wanted to. The final velocity of an object would be equal to the initial velocity plus acceleration times time interval. So put a little delta in front of that. So if I start at 0 meters per second and I'm accelerating at 5 meters per second for 2 seconds, that means after 1 second I'm going 5 meters per second. After 2 seconds I'm going 10 meters per second. If I already start at 3 meters per second and I'm accelerating at 5 meters per second every second, then 3 plus 5 times 2 means my final velocity would now be 13 meters per second. Another rearrangement of this, which is just algebra, is that my initial velocity is equal to my final velocity minus acceleration over that time interval. So these three things are really all the same formula. Probably this is the one you might have to think about, the Pivot Interactives labs. Finally, another way we can figure out acceleration, and it's a derived formula, and I'm not going to get into that right now, is this. Oops, hold on. X is position or distance sometimes, so we see that a lot in math as well. So change in position is equal to 1/2 multiplied by the acceleration of an object multiplied by time squared. And actually I won't put time squared, it really should be delta t, or time interval squared. If there's an initial velocity to an object, this gets a little more complicated, but I think for the Pivot Interactives lab I don't think it will. Why is it time squared? Well, there's a couple ways to explain that. If you think about the units for acceleration, which are meters per second, or meters per second squared, if I have units of time as seconds, and I square that, meters per second squared multiplied by seconds squared gives me units of meters, which do give me the correct units for distance or displacement. A lot of times what we can think about is using this for acceleration or solving this. So if I want to get A all by itself, divide both sides by half. That's the same as multiplying this side by 2. Divide by t squared. And that would be the acceleration of the object. And you might just see that as 2x over t squared. We'll sometimes get lazy with putting that delta symbol in there, noting that it's an interval. If you wanted to solve for time, be something like this. Whether you're moving vertically or horizontally, a lot of times people use the symbol x for, again, displacement or change in position, even if that's vertical. Sometimes you see that used as a y. So key formulas you might need to use for the Pivot Interactives lab, something like this, and possibly something like this. So if you know position, change in position and time interval, you can get acceleration by using this version of the formula. If you know change in velocity and time interval, you can get this. You can't just use average velocity divided by time to get acceleration, by the way. That'll be off by a factor of 2, which actually is why this formula has a half in it. So hopefully this is something that makes sense.